All right, top of the morning to everybody. Today we are finishing up the set of affine schemes and then getting into the topological space of affine schemes. So, should be a fun day. And yeah, cool. So, I guess we'll start with this exercise that says consider the map from C to C, which sends x to y is equal to x squared. So the source of the map is the kind of x-axis. And then target is the y line. Which really we can think of as looking something like this if it'll adjust itself. There we go. So this is the y line. This is the x line. So interpret the corresponding map of rings from C over y to C over x, which sends y to x squared. Verify that the preimage that I guess if we're calling we'll call this f, that f inverse of a is equal to plus or minus the square root of a in C. By identifying with the ideal generated by x minus a. And square root of a by x minus square root of a. So I guess it's that if we have this map cy to cx, it should induce it. Spec c over x to spec c over y, right?
That makes sense.
Um, And what that does is it sends x minus a to x minus the square root of a. And so we'll call this f star. And so essentially, if we have let a and c have x minus a spec c over x as a is congruent to 0 and c then f star of does that make sense?
Yes.
The way I've constructed that. I know I didn't like say a lot, but hopefully I wrote enough.
Yeah, that makes sense.
Yeah. I'm just gonna use the bathroom real quick. Do you so I'll be back in like a minute.
Okay.
All right. I'm back. You back?
Yep.
Um okay. So now we have a theorem let f1 through fn be over k in x many variables. No, I need to actually index this. Oh wait, not x, y. Such that so I'm talking through the first part of this theorem. Basically, if we can pick out the functions, I guess in like f1 through fn that generate j, and we can let them be contained in I in the image. So let j equal f1 through fn, and then I is equal to phi of j, or I guess really phi. It will say contains, it's fine. Then mod I is an injected map. No, it's a surjected map. And is that clear why this holds?
Yeah.
So, like,
Are we saying that J is a prime ideal?
um, Oh, I just realized that this needs to be, hold on. This needs to be phi inverse of F1. And it doesn't have to be prime.
Oh, okay.
Yeah. And so then I contains um, the ideal generated by F1 through Fn.
Oh, okay.
And then that induces spec. And I guess we can write out how it works. It sends you know, let me do this in blue. Sorry.
Mm-hmm.
It sends it sends prime ideals over to yeah, that's the map.
All right.
Where A is a prime ideal reduced I. Um, yeah, and then there's a part two to this theorem, which is that um, by uh, x minus a, x1 minus a1, x m minus am is equal to since phi inverse of a is Fi evaluated a point? Fi evaluated at points A. Does that make sense about how we get there from the construction?
Yes.
Okay, I'm pretty happy with that.
Yeah.
Um, so exercise picturing the affine n line over z to spec z given by the ring map z um if p is prime there exists a bijection um to oh, this is pi. I don't know how I didn't see that. So so Um, the thing that's throwing me for a loop here is that I would just write this as the ideal generated by P, but that's not right.
Mm.
Because FP has no such ideal. Um, I need to blow my nose real quick. I'll be right back.
Okay.
Okay. I think I figured out a bijection.
Good.
And then this translates over to A1
Bless you.
through AN mod P. Um, because this just gets sent. This is not equals to, this is the map.
Right.
Um, but it looks like, A1 through AN as a tuple. So, um, yeah.
Mm-hmm.
Okay. So there's the next kind of topic is functions are not determined by their values at points, the fault of nilpotence. So we conclude this section by describing some strange behavior. We are developing machinery that will let us bring our geometric intuition to algebra. And there is one serious point where your intuition will be false. So you should know now and adjust your intuition appropriately. As noted by Mumford, it is this aspect of schemes which was the most scandalous when Grothendieck defined them. Suppose we have a function, ring element, vanishing at all points. This is not necessarily the zero function. The translation of the question is the intersection of all prime ideals necessarily just zero? And that's actually a good question. Is the intersection of I and spec A necessarily zero? No. As is shown by the example of dual numbers, where I think this was the day that you had to leave early. I didn't really understand this example. Nope. There we go. Where epsilon is non-zero, but epsilon squared is equal to 0. Any function whose power is 0 certainly lies in the intersection of prime ideals. So, lies in the intersection of all prime ideals. So definition, such elements are called nilpotent, i.e. A and R is nilpotent if there exists S such that so
You want to go up just for a second?
yeah. I need to blow my nose again. So a little bit confused about why this is true or what the map is. Let me look this up. Mm. So this is accomplished if pi is a map like so. I'm going to call this pi star. Then the induced map happens by P gets mapped to the inverse image of B or of P. Um, and this is yeah. Um, um, and so then why this is a bijection. So let X and B be nilpotent with P a prime ideal, then zeros in P. And by Nullstellan shots, the S is in P implies X is in P. So if I consists of nilpotents, I is contained in this prime ideal P for every P in spec B. Does that make sense?
Yes.
And then surge activity comes from pi inverse of P mod I is equal to P. And then injectivity. Can we just hit that with trivial kernel? Yeah, we can. Kernel of pi star is equal to 0. Because it's all of the nilpotent elements.
Yeah.
Is um okay, and so then that's that. An associated theorem is that the nilpotents of B form an ideal called the nil radical, which is denoted by something like script eta. And which is contained in the intersection of all prime ideals. Oh, and actually, which is the intersection of all prime ideals. Geometrically, a function vanishes on spec A if and only if it is nilpotent. And that is a big theorem. Yeah. Um, and then a corollary is that two functions have the same values at points if they differ only if and only if they differ only by a nilpotent. Again, geometrically.
I'm not going back up, sorry.
Yeah. So if there are no non-zero nilpotents, then functions actually are determined by their values of points. And so this leads to a definition. A ring is reduced if and only if its no radical is the zero ideal. And this is the same condition as above. There are no non-zero nilpotents. Does that make sense? Oh, I just realized.
Yeah, can you just give me a second to get this down?
Yeah.
All right.
Cool. Um. Okay. So there's kind of a cool example.
Yeah.
Of nilpotents and their importance is let f of x be in k over x and work in k over x and epsilon. What is, sorry, mod epsilon squared? So, like I guess an example is we could do x squared in r over x. Well, f of x plus epsilon is equal to x plus epsilon squared, which is equal to x squared plus epsilon squared plus 2x epsilon. But this vanishes. That is equal to x squared plus 2x epsilon. We could do the same thing for x cubed. F of x plus epsilon is x squared plus 2x epsilon times x plus epsilon. X cubed plus epsilon x squared plus 2x squared plus
2x squared epsilon.
yeah. Um maybe like x squared minus 3x plus f of x plus epsilon is equal to x squared plus 2x epsilon minus 3x plus epsilon. Um, oh, we missed something up here.
It's 2x squared epsilon.
Yeah, which is then equal to x cubed plus 3x squared epsilon. There we go. And I'm just going to highlight that what falls out of this is that this,
Like the power rule.
yeah, it does differentiation in the epsilon term. So let's correct that here. This is equal to x squared minus 3x plus 2x epsilon. Or I'll write this as plus epsilon times 2x minus 3. And this is exactly the differential of x squared minus 3x.
Yeah.
So this leads to a cool theorem that df dx is equal to the epsilon terms of f of x plus epsilon. I think that that's a pretty cool theorem.
Yeah.
And it falls out of geometry. I need to blow my nose and my Apple Pencil needs to charge. So let's take 5.
Okay.
And come back at 8:45.
Okay.
Okay, I'm back. Garrett, you back?
All right, I'm back.
Awesome. Yeah, sorry for the slight delay. I got some coffee.
No problem.
Um, so yeah, this theorem that we just ended on was kind of like a hint at nilpotents are going to be used to store differential information later. Um, so now we're on to the section called visualizing schemes. And so for years, you've been able to picture the unit circle in the plane. You now have an idea of how to picture spec Z. If we are claiming to understand rings as geometric objects through the spec functor, then we should wish to develop geometric insight into them. To develop geometric intuition about schemes, it's helpful to have pictures in your mind, extending your intuition about geometric spaces you're already familiar with. As we go along, we will empirically develop some idea of what schemes should look like. This section summarizes what we have gleaned so far. Some mathematicians prefer to think completely algebraically and never think in terms of pictures. Others will be disturbed by the fact that this is an art, not a science. And finally, this hand waving will necessarily never be used in the rigorous development of the theory. For these reasons, you may wish to skip these sections. However, having the right picture in your mind can greatly help in understanding what facts should be true and how to prove them. Fitzgerald's exhortation on the importance of stretching one's mind is essential advice to a mathematician. The test of a first-rate intelligence is the ability to hold two opposed ideas in the mind at the same time and still retain the ability to function. Our starting point is the example of affine complex varieties, things cut out by equations involving a finite number of variables over C, and more generally, similar examples over arbitrary algebraically closed fields. We begin with notions that are intuitive, traditional points behaving the way you expect them to, and then add in the two features that are new and disturbing, generic points and non-reduced behavior. You can then extend this notion to seemingly different spaces, such as spec Z. Hilbert's weak Nullstellensatz shows that the traditional points are present as points of the scheme, and this carries over to any algebraically closed field. If the field is not algebraically closed, the traditional points are glued together into clumps by Galois conjugation. This is a geometric interpretation of Hilbert's Nullstellensatz. But we have some additional points to add to the structure. You should remember that they correspond to irreducible closed algebraic subsets. As motivation, consider the case of the complex affine plane. We had one for each such irreducible polynomial plus one corresponding to the entire plane. We will make closed precise when we define the Zariski topology in the next section. You may already have an idea of what irreducible should mean. By corresponding, mean that each closed irreducible subset has a corresponding point sitting on it called its generic point. It is a new point distinct from all the other points in the subset. This correspondence is described in 3.7f for spec A. Yeah. We don't know precisely where to draw the generic point, so we may stick it arbitrarily anywhere, but you should think of it as being almost everywhere, and in particular near every other point in the subset. We saw how points of spec of A mod I should be interpreted as a subset of spec A. So for example, when you see spec CXY mod, the ideal generated by x plus y, you shouldn't picture this just as a line, but also as a line in the xy plane. The choice of generators x and y for the algebra implies an inclusion into affine space. We saw how the points of the localization by a multiplicative subset, the points of the spectrum of that should be interpreted as subsets of spec A. The two most important cases were discussed. The points of the localization by a function correspond to the points of spec A where f doesn't vanish. And if P is a prime ideal, then the localization of A, the spectrum of that, is a shred of the space spec A near the subset corresponding to P, the prime ideal. The simplest non-trivial case of this is A is equal to K over X and P is equal to the ideal generated by X. And then he has a quote from Alice in Wonderland. If any one of them can explain it, said Alice. She had grown so large in the last few minutes that she wasn't a bit afraid of interrupting him. I'll give him sixpence. I don't believe that there's an atom of meaning in it. If there's no meaning in it, that saves the world a lot of trouble, you know, said the king, as we needn't try to find any. Pretty funny. I think that that's a good good transition. I just realized I left my water in the kitchen when I went to get coffee. Let me write down the section title and then let me run and grab my water.
All right.
Topology of affine schemes. All right. Okay. Um, so now we will introduce the Zariski topology on the spectrum of a ring, not just on varieties, right? Or affine space. Um, so consider the affine plane, which is in bijection with spec C, X, Y. In algebraic geometry, we will only be allowed to consider algebraic functions, i.e. polynomials in x and y. The locus where a polynomial vanishes should reasonably be a closed set, and the Zariski topology is defined by saying that only the sets we should consider closed should be these sets, and other sets forced to be closed by these. In other words, it's the coarsest topology, like the smallest topology, where these sets are closed. Yeah. In particular, although topologies are often described using open subsets, it will be more convenient for us to define this topology in terms of closed subsets. If S is a subset of A, define the algebraic set, the vanishing S as Z of S is equal to V of S is equal to the set of P in spec A such that S contained in P. Or rather, S is, yeah, there we go. Then it is the set of points the reason why I erased the Z is this is just kind of a we'll keep the Hartshorne notation separate from this notation. It is the set of points on which all elements of S are 0. Equals points which all elements of S are 0. Thus, vanishing at a point is in direct correspondence with contained in A prime. As an example, consider the vanishing of V, X, Y, Y, Z contained in the affine 3 space, which is spec X, Y, Z. Well, we think of this as solving all the points X, Y, Z such that X, Y is equal to Y, Z is equal to 0. Well, this is the same thing as saying that, Y times X minus Z is equal to 0. And so this is the set of all points where Y is equal to 0 and or X equals Z. Of the new points, we have the generic point of, so in terms of spec, the above condition holds, but we also have the generic point. The generic point of the xz plane, which is the ideal generated by y. But then we also have the generic point of the y-axis, which is and some polynomials, some curves in the xz plane. So does this make sense, like how this corresponds to the condition y equals 0, and this corresponds to the condition x equals z?
Yes.
And then this corresponds to both?
Yeah.
Yeah.
Yes.
Yeah. Another artifact of this is like the x-axis is contained in V of x, y, y, z, since the x-axis corresponds to when y equals z equals 0, which is the same thing as the point y comma z. And since we have y corresponding to 0, that means that like z must also correspond to 0. So we get Does that make sense in terms of that construction?
Yeah.
So, returning to the general situation, um, vanishing sets of ideals. Let me just adjust my so this is a theorem. If S is generated by S, then V of S, the vanishing of S is equal to the vanishing of the ideal of S. Yeah, and so we've actually already proved this. We just talked about it in a different way. This goes over to like talking about radical ideals and like early
Yeah.
Null plots. So what it's building up to here is that if you have the variety of like in Hartshorn, we have S is equal to the zero set of F1 through FR. But then if I is equal to F1 through FR, then VI is equal to V of F1 through FR. And then the big thing that I'm assuming we're going to talk about radical ideals, is that I of V of I, which corresponds to the ideal generated by the variety of the ideal, which is of course equal to the ideal generated like so, is called radical and is typically square root of I. And we proved some stuff about this in lecture 1, 25 lectures ago,
Wow.
which that's crazy to me.
Yeah.
So anyway, I'm just drawing the correspondence here between books. We actually were going to do a quick definition of the Zariski topology. So, Zariski topology on Spec. Varieties are closed for all S. And this is a topology. So to show that this is a topology, we would show that the empty set in Spec A are in here. So is it in A or is it in Spec A? I think it's in Spec A. That's in Spec A. Um, yeah. So, theorem. This is a topology, i.e., the empty set in Spec A are open in Spec A. If I over some index set J is a collection of ideals is equal to the variety of the sum of ideals. And then the union is equal to the product of ideals, which are linear combinations of products of generators. So linear combos of products generators. An example of this would be like x comma y multiplied by x squared y cubed is equal to the ideal generated by x cubed y, x squared y squared, x y cubed, and y to the fourth. If that makes sense.
Yeah, that makes sense.
And then the sum of ideals like this is just, the generators of I1, F11, F12, F1M, and then F21, F22, F22N. And yeah, this is a topology. And so this is that arbitrary unions are open, and this is that finite intersections are open. And the reason why it's switched, the reason why this is an intersection and this is a union, is because it's that arbitrary intersections are, or like arbitrary intersections of closed sets are closed. So like this is arb intersections of closed sets are closed. And this is arbitrary unions of closed. Or no, this is finite of closed sets are closed. And those are equivalent definitions for showing that something is a topology. So yeah. So theorem, the function for variety generation is inclusion reversing, i.e. if S1 is contained in S2, then the vanishing of S1 contains the vanishing of S2. And equality actually doesn't carry over, and this is the whole business of radical ideals. Definition. If I A is an ideal, its radical ideal is it's IVI, but it's the set of R and A such that R to the n is in I for some n in Z greater than 0. And this is equivalent to IVI, right? In terms of how Vakil has put this, so as an example, the no radical is the square root of the ideal generated by 0. And so I guess the theorem here is that this is an ideal. And this is actually something we proved a while ago. A theorem that's a little less obvious is that the vanishing of the square root, or the vanishing of the radical ideal, is the vanishing of the ideal. So again, where did we define it? There we go. These are all the points that contain the square root, and since this pretty clearly contains I, like this proof, square root I contains I. And so any vanishing that's going to happen has to be, so we've square root I is contained in V of I. And then to get the other inclusion, V of I is the set of all P spec A such that P is contained, or such that I is contained in P. But then, so let Q in VI, then I is contained in Q. But the vanishing square root of I is the set of P spec A such that root I is contained in P, and root I is the set R and A such that R to the n is an I for some n. And so basically this includes Q is in V squared I, since P is the coarsest, or since Q is the coarsest such thing for square root of I thing ideal. Containing I. Coarsest meaning smallest.
Mhm.
For radical containing I, then I is, or the root I is contained in I, and the vanishing of root I contains the vanishing of I. So, does that make sense?
Yes.
Um, Now, as a follow-up definition, an ideal is radical if I is equal to square root of I. And just as a quick proposition, the radical of a radical ideal is just the radical ideal. It already contains everything. And then prime ideals are radical. And that has to do with this line. I guess I would say this. Then two useful consequences of all of this. So the intersection of ideals squared is contained in the product of the ideals is contained in the intersection. And then also the vanishing of the product is contained in the vanishing of the intersection. Is equal to. And then is equal to, and we'll prove this later, the vanishing of I union the vanishing of J. So as a theorem that will probably end by proving
Hang on, you mind
square.
going back up real quick?
Oh yeah.
Thank you.
Sorry. Let me send a Teams invite so
Yeah.
Alex and Arseni as well. To Garrett Rocca, Alex, Artie, and Arseni. Oops, that was, yeah, okay. Let me know when you're ready.
Yeah, I'm good.
Okay. Okay. So this theorem, I is the intersection of prime ideals P, such that P contains I. So yeah, actually, I think this follows pretty easily. So these are all of the things. It's all of the R and A. So such that R to the N is in I for some positive N. And so then if I is the prime ideal, then or no, if P is a prime ideal, the point P is distinguished by the no radical on P. Like if it's trivial, then it's determined by its points. If the no radical of P is 0, P is determined by points in A, and so P is n squared of I. If the no radical is non-zero, we'll call P Q. And Q intersect P from the previous thing, is n squared of I, which is the intersection. Basically we're saying that it's the intersection of the non-zero no radical regions with the zero no radical. And then since arbitrary intersections of closed sets are closed, all such intersections is closed, and course on I. And I think that that proves it. Does that make sense to you as a proof technique?
Yeah.
Okay. then that's all I think I want to cover today.
Okay.
So we'll pick up next time, finishing off this section, and then we'll talk about a base of the Zariski topology, and then some topological notions. Yeah. Cool. All right. I'll go ahead and end the recording.